In this lecture, we're going to discuss program profiling. Profiling, by definition from the American Heritage Dictionary, is defined as the formal summary or analysis of data representing distinctive features or characteristics. Program profiling is performing the summary or analysis of dynamic information of a program in attempt to extract or summarize a program's behavior to give us a view of what the program is doing when it runs at execution time. There are many types of profiling. The two ways of distinguishing profiling are first offline versus online. Offline means that you're going to collect the information from the program by executing the program ahead of time before a user is using it. You have plenty of time because the profile is not being collected while the user is using your program. So you can perform a much more detailed analysis. You can impose a lot higher overhead to collect this behavior. Offline has a downside also, which is when you choose an input and collect a profile based on the execution of that input, it's going to be input specific. So if you execute different inputs, you may see different execution characteristics. So offline profiling has a downside in that you are only getting information that is reflective of the execution characteristics for the inputs that you give to the program. And so if you have a program that just happens to have similar execution characteristics across inputs, you're good. If not, you're going to have to profile lots and lots of different inputs to make sure you're capturing the behavior you're after. Online means that you're collecting profile information while users are using the program or while the program is executing in production. And in this case, you have much less time, much less freedom to introduce overhead because it may disturb the performance or the user's perception of program performance via slowdown and overhead. Online is nice because it still is input specific, but you're capturing behavior for that particular input, which you can use immediately to say optimize the program for the current hotspots of this program with these inputs. The other way of distinguishing profiling is with the terms exhaustive versus sample-based. Exhaustive sampling means that you're going to measure all events of some particular characteristic. Sample-based means you're going to just collect a subset of these events for a particular characteristic. Sample-based is estimation. So you're not going to have a complete view of the characteristic that you're after, but you a lot of times can get a little bit of information and use that information to extrapolate the full behavior or the full set of characteristics that you're looking for. Sampling is much lower overhead because you're just doing less work. Exhaustive, it gives you a truth value in some cases for some types of characterizations. And if you're using a sample-based technique, the best way to determine how far away your sample is from the exhaustive profile is to take the difference. Again, this will give you the error that is involved in the estimation you're making with the sample. Online profiling is commonly done using samples so that to keep the overhead low and to prevent slowdown from happening as much as possible, but it can be inaccurate as well, so you have to manage that trade-off. The first question to ask when we're talking about profiling is why we should profile. Profiling is used for a wide variety of uses to interested parties like developers, systems optimizers, people who are interested in performance and utilization of their systems, as well as companies interested in making their programs run faster or use less battery life to optimize the program with. So, why profile? The first one is to characterize program behavior. We can the programs can be very complex when they run, and our hardware and operating systems are also very complex. So it's hard to understand what your program is doing when it runs, and so profiles can help with that. Can describe how programs behave. We can use profiles to guide the design of programmer productivity tools, the runtime, the hardware and software that underlie the program. We can also use program behavior to guide test generation to figure out what parts of the program to test and what parts of the program you can get away with testing less, since there may be overlap in tests and what they capture. The next reason why to profile is to capture specific or unusual behavior. You can identify bugs this way by pinpointing the areas of your code that are infrequently executed, because you're going to probably test the areas that are frequently executed because those are the easiest to test. But there may be parts of the code that are cold and not exercised frequently, and profiling can help you identify those regions of code. Profiling can also help you identify security attacks, anomalies, can detect intrusions, and can help with testing, as I mentioned earlier, and just to log information so that when there is a problem, we can go back and reflect on what the program was doing. Logging is just another type of profiling. Another reason to profile is to improve program performance or to decrease battery life that your program is consuming. It's also really important and used frequently to track performance regressions. This means that as you develop an application, it has a certain performance signature. If that changes negatively over time due to commits from developers, you can identify and track which commits hurt performance and investigate whether those can be corrected or if those are really necessary. So the common technique here is you're going to time different parts of the program to figure out where the time is being spent. If you look at how programs behave, typically there's usually an 80-20 rule or a 90-10 rule where 20% of the code contributes to 80% of the execution time. So if you can focus in on the 20% that contributes most to performance, you can optimize the program with bigger payoff, less work for more payoff. You can hand optimize with profiling information, and you can perform automatic or feedback directed optimization, like the adaptive system we spoke about in an earlier class, where you want to target the hot code with optimization. You want to identify opportunities to inline, because it may be hard to figure out what exactly you want to inline and when. And if you want to move instructions around to take advantage of your processor resources better, you can use information about how your programs behave to restructure your programs to do so. Profiling is becoming increasingly important for speculative optimization. This is where we're going to make guesses about the future behavior, and we're going to optimize based on those guesses. And if our guesses are wrong, we're going to have to undo the work that we've done. And so if we have a good profile of the execution characteristics, we will have a better chance at ensuring that our guesses or our predictions are correct. With the hardware trends today that are moving towards more simplicity and multiple contexts, we're going to be doing less speculation in hardware, and thus we'll have more of an opportunity to do it in software, and we'll need to extract performance out of these systems. The next question to ask is what to profile. There's lots of things in the program to profile. You need to really reflect on what you want to profile, what information you want to extract from the program, and identify the best way to extract that information, that is, with the least amount of overhead and the highest accuracy. The first thing we could profile is just individual instructions. We can look at memory accesses. We can look at, and that would lend insight into how the caching system is working, and the paging or the garbage collector, what bugs we might be introducing, and a lot more. We may want to look at loops and identify, what operations are being performed in loops. If we don't need individual instructions, but we need to understand the control flow, such as that which is exposed by loops, we can just capture basic blocks. Instead of having an overhead on each individual instruction, this way we only have overhead on a basic block. And this is how you should be thinking. Figure out what you want to measure, and then we can identify the least intrusive way of extracting that information at runtime. So the other things that we can profile are paths. We have methods, and typically methods contain multiple paths, but only a small number of those paths are taken when the program executes. If we can profile paths, we can identify those paths and optimize accordingly. We can instrument function calls and returns to identify relationships between callers and callees. We can profile memory allocation and garbage collection characteristics. We can profile the interfaces, the methods that through which different components in the system speak, communicate. Maybe you're interested in how often Python talks to C code and uses that foreign function interface between Python and C. We maybe want to just measure resource use. How much CPU are we using? How much disk or I/O are we performing? And you may be interested in the runtime services instead of the program itself, the GC or the compiler, or our access to the operating system. Finally, we may be interested in just the user interactivity and the user experience, and there's lots of ways you can measure this as well.